Hi everyone, Mr. Kalonji here. In this short lesson, we are going to talk about probability distribution, and at the end of this series of lesson, I will expect us to understand the difference between discrete probability and continuous probability and all the different type of calculations that are involved in those two major groups. All right, so the definition of probability distribution is just a list of all the possible outcomes of a random variable and their associated probability occurrence. So when we talk about probability distribution, what we're trying to understand here is we are moving away from this empirical type of probability, which we really worked in our previous chapters. For instance, you have a frequency distribution table, and based on the values in this table and the different categories, you get to work out a probability. Now, what we're going to is more of some of the mathematical formulas. So what do I mean by this is most of the time you notice that there's a specific pattern that occurs within various type of event. And once you establish these specific patterns, we can actually work out a probability of that event with this type of patterns in mind. But of course, because we have two major type of numerical data and probability has to do with numbers, what we'll notice is that probability will be divided into discrete probability distribution, and the next one is continuous probability, which we're going to look at next in another video. So the first set of attention is going to be what is discrete probability distribution and how does that work? Again, when you read from the textbook the definition of a discrete probability distribution, we are assuming that the outcome of a random variable and a study can only take specific values, and those values are integers. That's the reason why this is known as a discrete probability. And some of the examples of discrete probability or discrete data, which we've already covered, will be a math class can only have 1, 2, 3, 4, 5 number of students, a bookshop, a machine can produce a defective item in a shift, a company can have employee, and so forth. So basically anything that you cannot put a comma or you cannot have is more likely to be your discrete data. As a result, we can work out a discrete probability distribution. When we look at discrete probability distribution, there is a non-zero probability for each possible outcome. So the probability is 0 for values of the random variable that are not in the sample space. So that's what that means. And the two type of probability distribution here are going to be binomial probability distribution, and you also have what we refer to as the Poisson probability distribution. So now, without wasting much time in all this theoretical concept, let's start with binomial probability and understand what is this binomial. For a probability to be considered binomial, it has to meet 4 specific criteria: 1, 2, 3, and 4. And in fact, when we break the term binomial, you see that there's bi, which means 2, and nomial. So by definition, this probability works on 2 set of outcomes. Nothing less, nothing more. One is going to be a success of a specific event, and the second one is going to be failure. Okay, so those are the main things. So binomial, just remember bi, 2. So you either have success or you have failure. All right, so let me just clean this up a little bit and we are going to dive deep into it. Now, looking at any scenario where you have to work out a probability distribution, you have to look out for those specific events. The first one is that your random variable needs to be observed n number of times. Okay, So you have to observe that variable in the n number of time. Then you only have two mutually exclusive, which means that they cannot occur at the same time, and collectively exhaustive outcome, which means that when you add the probability of success plus the probability of failure, it's going to give you 1. Mutually exclusive means that you could have a probability of success or you could have a probability of failure, but not both of them at the same time. So that's what we refer to as mutually exclusive and collectively exhaustive. And again, as I said, those two outcomes are labeled as success and failure. For instance, if you're working in a factory, it's either the product is defective or it's not defective, nothing in between. When you're looking at a work situation, an employee is absent or not absent from work. There's nothing in between. A consumer would prefer brand A or not brand A. So you see the difference here when the difference is like when you say brand A or not brand A. I didn't say brand A or not brand B, and that is very important because each outcome would have an associated probability. So the success will have a probability assigned to it, and the probability of failure is just going to be 1 minus P, which is our complementary rule that was covered in the previous chapter as well. So for instance, if the probability of success or having an employee maybe not showing up to work, let's say that is a success. If it's 0.5, then the probability of failure will be 1 minus 0.5, which is also at 0.5. I hope you understand that. So that is the third criteria for us to have a binomial probability distribution. The last one is the objects are assumed to be independent of each other, meaning that the P remains constant for each sampled object, which means that at every trial, every time we measure this, the outcome of one does not affect the outcome of another. Let's say you do have a store. This is your store. You sell 3 products. This is, let's say, tomato. You have banana and maybe peach or pear, whatever this fruit is. If you know that people maybe there's a specific product, 3 out of 4 people will prefer this, means that when person 1 comes and selects this, it's going to be independent of the second person coming and selecting this again. They don't talk to each other and it's independent. So that's what is meant by the sentence that the objects are assumed to be independent of each other. So the probability remains constant for each object. Once all these 4 conditions are satisfied, that's when now one can choose to ask or address the binomial question. And what is your binomial question here? Your binomial question is, what is the probability that X success will occur in a random drawn sample of n object? And of course, once you ask that question, you can easily work out the formula where n is going to be your sample size, then for instance which is the number of independent trials of what you have observed, right? And X is the number of success of that outcome in the independently drawn object. Then you have the probability P, which is the probability of success. So this success would have a probability, obviously. Then 1 minus P is the probability of failure of a single independent object. So the X value represents the number of success outcome that can observe in a trial, and it's also known or generally referred to as your domain. And of course, there's in-depth explanation that is going to make more sense when you read later on. For instance, the number of success outcome cannot exceed the number of trials. So the domain for the binomial probability is limited to all the integer value, including 0 up to the sample size. So this last sentence may seem a little bit confusing, but what I'll suggest is that you can return to it once we've looked at specific examples. So in the next video, please pay attention to the example that we're going to have on how to solve this binomial probability distribution.